Hello, in this video we're going to study the Rydberg equation. That's the equation seen here at the top of the page. In this equation we have on the left side 1 over lambda. Now lambda represents the wavelength of light emitted from hydrogen gas in a discharge tube. We know from experimental data that when we look at the wavelengths of lines emitted from a hydrogen discharge tube, that in the visible region of the spectrum we see 4 lines. One of those lines is very, very dim and difficult to see, but there are 4 hydrogen lines in the visible region of the spectrum. This equation was determined based on the wavelengths of those lines, and this equation was actually derived before the advent of quantum theory, before we knew about energy levels. But we now know that in this equation, the wavelength of lines is related to energy levels for the atom. And those are represented by these n values here, which are integer values 1 and above. So in this situation, we can consider a case where we've got energy levels, and let's try to draw them here. So I'm going to have an energy level here, and then we'll have another energy level here. All right, and let's just put another energy level here, and let's just put one up here at the top, as we see. All right, so we've got these energy levels, and these represent energies of electrons in the hydrogen atom. Okay, so the bottom one we're going to call n equal 1, that's the lowest energy level, and then there's n equal 2, n equal 3, n equal 4. And again, this equation was derived before we knew about quantum theory and we knew about energy levels in atoms. It was empirically derived, but it does fit with the model of the atom that's developed through quantum theory. First, from Bohr, that we've already talked about the Bohr model of the atom, where each of these n values corresponds to orbits, discrete orbits of the electrons around the nucleus. We know, of course, now that that is not the correct picture of the atomic structure, that electrons don't have discrete orbits, that electrons do not have trajectories, specific trajectories. What we know now, of course, is that electrons, the description of the electronic structure of an atom is one of electron density and what we sometimes refer to as electron clouds. Nonetheless, each of these energy levels is in fact a valid description of the electronic energies in the atoms. All right, so what's going on here when we look at the various colors that are emitted in the hydrogen spectrum? All right, so here is the hydrogen emission spectrum, at least the visible, in the visible region of our spectrum. And what you'll note is that there are 4 colors. And again, this is the whole thing that was mysterious to scientists at the time, because that rather than having a continuous range of colors in the spectrum, there are specific discrete lines that appear in the spectrum. And really before quantum theory, it wasn't understood why that was the case. We had the equation, the Rydberg equation, that was able to predict the positions of the lines, but the theoretical background, the reason for it, wasn't known until the advent of quantum theory and the specific advent of energy levels and Bohr orbits. And we'll get back to that in a couple of minutes. So we've got these lines here at red line at 656. And there's a green one, and there's a blue one at 410. There's a violet one. And the reality is, of course, in the data that we've collected, that violet line is so weak that we didn't see it with the devices that we had to collect the data. So we have just 3 lines that we're going to be using to analyze: the red line, the green line, and the blue line when dealing with that. So just going to erase these here. So to clean things up. So what's going on with the emission of the lines? Well, in these situations, what's happening is that in the discharge tube, the electrical discharge is exciting electrons in the hydrogen atom to higher energy orbits, into higher energy levels. And the Bohr model predicted that each one of these levels corresponded to a discrete orbit. Of course, we know that the Bohr model is incorrect, that electrons do not have discrete orbit trajectories. We can only predict with certain probabilities where we might find the electron, but we can say nothing about its trajectory at all. So we talk about electron shells, we talk about electron clouds, we talk about electron density, but we don't talk about electron orbits because that's not an accurate prediction of atomic structure. Nonetheless, we do have energy levels corresponding to electrons, and the lowest energy level, which is indicated by n equal 1 here, indicated by n equal 1, is where electrons, the vast majority of electrons, the vast majority of hydrogen atoms will have their electrons in the lowest energy level because that's the most stable. All right. But again, when we pass an electrical discharge through it, it energizes the electrons, and it may take them up to, say, n equal 2. Right. Now, this is an unstable situation. The electrons are in higher energy, and lower energy is favored. So they will emit a photon of light, and they will, in the process, collapse back down to a lower energy level, n equal 1. So we had an electron at n equal 2. It's going to emit a photon, which carries away the excess energy, and so the electron can come back to the lowest, most stable energy level. Now, the energy of the photon is going to be the energy that's lost by the electron. So if we take the energy of level 2 minus the energy of level 1, that's equal to the energy of our photon that's emitted. And we know, based on additional data collected at the beginning of the 20th century, that the behavior of light seems to also, while we knew it was wave-like, that these other experiments, blackbody radiation, for example, the photoelectric effect, which we talked about very briefly, seem to indicate that light also consisted of a collection of particles, which we call photons, and the photon energies are related to the frequency of the light. That's the frequency. And the frequency, of course, and the relationship between the frequency and the wavelength of light is indicated here, okay, as hc over lambda. And that's simply because the speed of light, which is c, is equal to the product of the frequency and the wavelength. That's true of all waves. The product, if you take the frequency of a wave, you're watching a wave, how many times does it pass by per second? How many waves pass by per second? That's the frequency of the wave. The wavelength is the distance between the crests of the wave. You take the frequency times the wavelength, that's always equal to the speed at which the wave is propagating. So, for example, sound, if I take the wavelength of a sound wave and multiply it by its frequency, that product is the speed of sound. In the case of light, it's obviously the speed of light. And again, so c is the speed of light, and h is what's called Planck's constant, and we'll take a look at those values a little bit later. We've already talked about those, but that's the basic idea. So the energy of the photon is equal to the difference in energy. E2 minus E1 is the energy that's lost by the electron, and the energy of the photon is equal to that, and that's related to the wavelength. Now, this is where the Rydberg equation comes into play, because the Rydberg equation says that the reciprocal of that wavelength is equal to this constant times 1 over the square, the difference between the square, 1 over the squares of the energy level. So in this case, if we're going from level 2 to level 1, then it's going to be 1 over 1 squared minus 1 over 2 squared. All right? And That, of course, is 1 minus 1/4, which is just 0.75. All right. So that's what the Rydberg equation tells us, is it relates the wavelength to the energy levels that are involved in that transition. Okay. So let's do a calculation here for this particular one. If we go look up the Rydberg constant, which is actually what you're going to be determining based on the data in this experiment, we can calculate the wavelength. So if we look up the Rydberg constant, and we're going to find that it has a value 109,678 centimeters to the -1, inverse centimeters, which spectroscopists will call wave numbers. You hang around spectroscopists, you'll hear them referring to wave numbers all the time, and when they refer to wave numbers, what they're talking about is reciprocal centimeters or inverse centimeters or centimeters to the -1, however you want to refer to that. So that's how that's used. All right, so we're going to take that and we're going to go ahead and we're going to use this information to actually calculate what the wavelength emitted corresponding to this transition from level 2 to level 1. So it's going to be 109,678 wave numbers times 0.75. So we can get our calculators and do that. I'm going to get out Excel here because it's time to just, we're going to have to use Excel actually to do these calculations and to fit the data anyway. So if you're familiar with Excel, great, but if not, this will be this will be a refresher or an introduction to how to use Excel to do calculations. You can, of course, do this on your calculator, but it's nice to have something like Excel for these calculations because you can save it in a file, you can come back to it to do additional calculations, or it's easy to actually go back in to see if you've made a mistake. All right, so we're going to go back and just a reminder, what we're going to do is we're going to do this calculation here in Excel. All right, so I'm going to move this off to the side a little bit so we can see that. All right, so the way we start a calculation in Excel is to use the equal sign. All right, that's telling it we're going to enter a formula, and this is a formula, and we're going to enter our Rydberg constant 109,678. Now Excel doesn't know units, and so you'll have to keep that in mind when we do these calculations. It's important that we note the units. And to multiply, we're just going to use the asterisk here. So times, all right, and 0.75 is what we're multiplying it by, so 0.75. And then we just hit enter, all right, and we get this value of 82258.5. So that's what we got, is 1 over lambda, 1 over the wavelength, is 82258.5. What are the units? The units are going to be the units of the Rydberg constant, and so that's centimeters to the -1 is what we've got there. All right, but that's the reciprocal of the wavelength. The question is, what is a wavelength? How do we get the wavelength? Well, to get the wavelength, what we're going to do is we're just going to take the reciprocal of both sides of the equation. So our wavelength is 1 over that. Okay, and again, you can do that in your calculator. One of the nice things about programs like Excel is that we don't have to retype things. We can just enter the formula for the calculation, and we can reference a particular cell. So for example, this would be equals, all right, 1 divided by, and I'm just going to click on cell A1. Now you'll notice that the cells in Excel have a column represented by a letter and a row representing a number, and so this is cell A1, and you'll see when I click on that, that's in fact what it enters in my formula. And now if I just hit enter, all right, there is the result. Okay, so let's go ahead and type that in. It is, and it's in scientific notation, 1.21 568. E to the minus 5 means it's 10 to the minus 5. What are the units? Well, the Rydberg constant was inverse centimeters, and when we take the reciprocal of that, that means we have units of centimeters. So there's our wavelength in centimeters. Okay. All right, so what does that tell us? Okay, where are we going from here? Well, at this point, what we'd like to do is convert that to nanometers, because our spectrum, for example, the visible spectrum here, up here, is in nanometers. So how does this relate to nanometers? And in order to do that, we need to know how nanometers relate to centimeters. Okay, we know that, and I'm just going to make my Excel document disappear here for a second. We know that 1 nanometer is 10 to the minus 9 meters. All right. We also know that 1 centimeter is 10 to the minus 2 meters. All right. So 1 nanometer is equal to 10 to the minus 7 centimeters. And that's the relationship we need to know, because our wavelength value here is in centimeters. So how do we do that conversion? I'm going to go ahead and type this in again. And the conversion factor then is basically how many nanometers are in a centimeter, or how many centimeters are in a nanometer. And that's our conversion factor. 1 nanometer is 10 to the minus 7 centimeters. How do I know to put the centimeters on the bottom here in the denominators? Because that way it cancels out. Centimeters divided by centimeters cancel. And so I'm going to get a number here, okay, that is in nanometers. That's going to be my result. So when I multiply this out, what I'm going to get is 1.21568 times 10 to the second, and you can multiply this out yourself just to make sure that this is clear to you. Or if we wanted to just shorten it, it's 121.568. So not using scientific notation, it's 121.568 nanometers. Okay, that's the wavelength corresponding to the emission from level 2 up here to level 1. Now you'll notice that 121.568 nanometers is way over here on this little spectrum. It's much shorter wavelength than what we see here. And so it is not in the visible region of the spectrum. In fact, the visible region of the spectrum we usually define as going from 400 nanometers to 700 nanometers. That's loosely how we define the visible, that range of wavelengths that we can detect with our eyes. So it's much shorter wavelength than the visible region. In fact, this is ultraviolet. So that emission from level 2 to level 1 corresponds to an ultraviolet photon, which we wouldn't see. All right, but that's a basic calculation that we're going to do here. That's how the Rydberg equation is used to calculate the wavelength, and that's the relationship between the energy levels that's important. All right, so I'm going to pause here. We're going to come back a little bit later and take a look at some of the other transitions that are occurring, and then how we're going to use our data to determine the Rydberg constant in this experiment that we have done. So I'll be back in a little bit. So let's just review a little bit at this point. What we just calculated was the wavelength corresponding to the emission that occurs when an electron goes from the n equal 2 level to the n equal 1 level. So let's figure out, and what we determined that this was in the ultraviolet region of the spectrum. So then the question is going to be, where do these visible lines, what do they correspond to? So let's just do one calculation there. I'm just going to go through this very quickly just to review. I'm not going to go through all the steps that I went through in the previous calculation, but it does turn out, as we'll see, that the red line that's here in the spectrum corresponds to a transition from n equal 3 to n equal 2. And the green line is going to correspond to a transition from n equal 4 to n equal 2. All right. So let's do the 3 to 2 calculation really fast just to prove that that's the case. So if we're going from level 3 to level 2, then what we're talking about is the Rydberg equation is going to be 1 over lambda equal to the Rydberg constant times 1 over 2 squared minus 1 over 3 squared. And again, that's level 2 to level 3. All right? So that's going to be the constant times 1/4 minus 1/9. Okay? And so let's go ahead and do that in Excel. All right? So let's bring up our Excel document that we had out here before. All right, and so now we're talking about the 3 to 2. So I'm going to go ahead and just go ahead and type this in like we did over here. That we're going to have our Rydberg constant. So we start with an equal sign. And then we have a Rydberg constant. One of the things that you're going to learn, and maybe I should show you how to do this because this may be something that you haven't done before. You need a refresher on how to do these kinds of calculations so you don't have to enter the same numbers all the time. So we can just enter. So let's just say I'm going to enter the Rydberg constant, and I'm going to just label this RH. And by the way, if you really dig deep into Excel, you can format things. So I could, for example, make that a subscript, but I'm not going to bother with that right now. And I'm just going to give it a label, and I'm going to then enter the value here. So you can label columns, you can format things in a way that you can actually create a document that is actually very attractive if you learn how to use all these nice features of Excel. And again, we're not going to do that right now. So I'm actually going to just give this 109,678. I'm going to list it there. And I'm going to enter just to make sure it's input. And now I'm going to do a 3 to 2 transition. I'm just going to type 3 to 2 here just to label things. And this is going to be the equal sign. And now rather than typing in the Rydberg constant, and the reason you would do this is if you are going to use the Rydberg constant repeatedly in a number of different calculations. I'm just going to refer to that. Now, here is the tricky thing about this and features of Excel that you will need to be aware of if you start doing a lot of different calculations in Excel. And that is that if I'm using the same constant and I'm going to be using that in a number of different, copying the equation in a number of different places, sometimes it's very useful. Oops, that's not what I wanted to do. Let's go back here. All right. Sometimes it's actually useful to put dollar signs here. And there's a shortcut key you can use for that, but putting dollar signs there, and what that does is it makes it what's called an absolute address. And the meaning for this, it's not necessary for the calculation that we're doing right now, so I'm not going to go into it and explain it at this point, but sometimes that's a useful thing to be able to do. And so then I'm going to multiply it by, they're all there. Okay, so now we're going to hit the asterisk to multiply it. And now that you'll remember, let me slide this over a little bit so that you can go back to see where we were. It's going to be 1/4 minus 1/9 is what we're going to enter here in this case. So I'm just going to go ahead and, in parentheses, 1 divided by 4 minus, oops, there we go, minus 1 divided by 9. Okay, and so then I can just hit enter, and I get my calculation. And so this is then the reciprocal wavelength that I get from that. So let's go ahead and write this down here. So our reciprocal wavelength is 15233.05556. And again, the units are going to be inverse centimeters. So now we're going to go ahead and take the reciprocal of that. We're going to do that the same way we did before. And just hit enter. And there we have our number, which is 6.56, I'm just going to round off here, times 10 to the minus 5 centimeters, right? And using the same thing, doing it the same way here. Let's get that out of the way so you can see. So doing the same thing that we did up here, we can see that 10 to the minus 5 is going to become, in terms of nanometers, 10 to the second. So it's going to be 6.565 times 10 to the second nanometers, or 656.5 nanometers. This is what we calculated for that transition. And again, what we're talking about is a transition that goes from level 3 to level 2. And then if we look at the line in the spectrum, it is indeed 656 nanometers, so that calculation worked really well, right? As we would expect, because the Rydberg constant was determined in order to fit the data. So it turns out that a Rydberg constant can be calculated theoretically with the Bohr model of the atom. But again, as I've said earlier in this video, that the original equation was derived based on the data. So that worked really, really well. Okay, so now we know how to use the Rydberg constant to calculate the wavelength. Now the question is, what am I going to do to calculate the Rydberg constant given the data that I have? All right, and I'm going to get you started on this, but I'm not going to go into it in great detail at this point, because I want you to think about this yourself and how you're going to work through this and going to do Excel. So I'm actually going to stop at this point here in this discussion of the Rydberg constant. And in the next video, what I'm going to do is run through how to do basic calculations and graphical analysis excuse me, in Excel. And then we'll talk a little bit about how we're going to apply it to this particular system. And let you think about that and see if you can work it out yourself. So that's where we are right now. That's the plan for the next time. So stay tuned.